For good measure, let's look at another paper that talks about IOD and El Nino. This is about the influence of the state of the Indian Ocean dipole on the following year's El Nino. So we are now talking about similar thing. Last podcast we talked about the paper that discussed how the strong western pole of the IOD influences the decay of El Nino in the following year, which is also following year's El Nino state, right? Could go into La Nina or linger in a fast and slow decaying El Ninos. Here it's slightly different, so let's see what it has to say. El Nino Southern Oscillation consists of irregular episodes from warm El Nino and cold La Nina conditions in the tropical Pacific Ocean with significant global socioeconomic and environmental impacts. Introductory statement. Nevertheless, forecasting ENSO at lead times longer than a few months remains a challenge. There's something called a spring predictability barrier. So if you predict an El Nino before March, April, May, then the system gets noisy during March, April, May, and then the skill of the forecast may not be very high. That's the general idea. Like the Pacific Ocean, the Indian Ocean also shows intraannual climate fluctuations, which are known as the Indian Ocean dipole. Positive phases of the Indian Ocean dipole tend to co-occur with El Nino, and negative phases with La Nina. So positive IOD is when you have cooling in the eastern Indian Ocean, warming in the west, and the other way for negative phase of IOD, whereas in the Pacific, east is warm in the positive phase of ENSO and cold in the negative phase of ENSO. El Nino and La Nina. Okay, historic accident. Here, we show using a simple forecast model that in addition to this link, a negative phase of the Indian Ocean dipole anomaly is an efficient predictor of El Nino 14 months before its peak. And similarly, a positive phase in the Indian Ocean dipole often precedes La Nina. Observations and model analysis suggest that the Indian Ocean dipole modulates the strength of the Walker circulation in autumn. Makes sense. The quick demise of the Indian Ocean dipole anomaly in November, December. Remember, IOD peaks in SON, and by December, usually it's gone. Then this induces a sudden collapse of anomalous zonal winds over the Pacific Ocean, which leads to the development of El Nino and La Nina. So we are still talking about decaying or El Nino decaying into La Nina or it's La Nina evolving and vice versa, right? Our study suggests that improvements in the observing system in the Indian Ocean region and better simulations of its intraannual climate variability will benefit ENSO forecasts. So in this case, if the model is doing El Nino well, but not the IOD, which is not uncommon in models, then you can try to understand why the model doesn't do the IOD. Typically, Indian Ocean thermocline is shallower in the west and deeper in the east as opposed to the Atlantic and Pacific Ocean where it's shallower in the east and deeper in the west, and models tend to have a bias in this. And if you don't have the thermocline slope correctly done, then you can't do the IOD either, but there are many coupled feedbacks, so chicken and egg is always an issue, and we don't know whether Pacific errors creep into the Indian Ocean in the models as well. So this is the IOD index as a precursor of the following year's ENSO state. Lag correlations between IOD in September to November of year 0 and ENSO in deceased, so that's the following year. The correlation skill, so let's look at this one here. Lag correlations going from minus 0.7 or so to plus 0.7, and the lags go in years from minus 18 months, so year minus 1, El Nino is speaking here, you're in the previous year and the following year, but all the way into year 2, year 0 is here. So ENSO before IOD, so you are seeing the correlations are low, then correlation jumps, ENSO after IOD, so this is the year of IOD peak, not necessarily El Nino peak. So this is year 1 ENSO peak. So the correlation is quite negative and obviously statistically significant. And then in year 2, So you are starting in year -1. Year 0 is when IOD peaks. Year 1 is when ENSO peaks, and then year 2 when the correlation again dies away. Okay, so here you are looking at the hindcast correlation skill. Basically, they are combining IOD and the warm water volume in the Pacific. Remember, we talked about recharge discharge. We are basically releasing warm water during an El Nino and recharging during a La Nina or normal conditions, which is what we call warm water volume. Without going too much into the details, basically they are arguing that IOD plus warm water volume can be combined to produce El Nino forecasts 18 months before. If you can use the relations between the state of the IOD here, IOD peak, and ENSO peak, and you can see that the hindcast correlation skill is very high and remains steady for a long time, whereas if you just use warm water volume and winds during February, March, April, like westerly wind bursts, then the skill drops off very quickly, whereas here the skill persists if you use IOD plus WWV or WWV of the SON when the IOD peaks. Okay, you get the point. Niño 3.4 SST and hindcast with IOD plus WWV, and they are claiming that they can make very good correlations. And the general tendency is that when you make hindcast experiments, maybe knowing the answer helps, so you get good skills, but as soon as you make a real forecast, then boom, the skills are not always so high. El Nino skill is consistently high, but remember, it's only for strong events. We have seen that plot of recharge discharge with thermocline anomalies and Niño 3 anomalies. When the El Ninos hover around the 0, point in the phase diagram, stochastic forcing can make it go in many directions, and internal variability, etc., play a role, right? So here again, just separating WWV contribution and IOD contribution, and the point essentially is that IOD of the previous year, the state of the IOD of this year, can help El Nino evolution and prediction of the next year. You can go and read the paper to see. Now we were already arguing whether IOD and El Nino are independent of each other when they co-occur, but now they are talking about previous year's IOD and predictions, as opposed to the previous paper, which was talking about the impact of IOD into ENSO decay in the following year. So this is the longitude time section of the Indo-Pacific anomalies associated with a negative IOD. So you are starting again with year 0 when here is the Indian Ocean, 40 east is East African coast. Here you have the maritime continent. Here is the coast of South America. So you can see that there is IOD in this year 0, and then you have El Nino evolving here in year 1. Okay, so these are the SST anomalies. So this is for observed SST. In B, we are looking at 0 to 300 meter oceanic temperature. So you are looking at the associated signatures in the heat content. So you can see heat content is discharged. So you have warm anomalies here and raised thermocline and negative heat content anomalies in the upper ocean here. In C, we are looking at zonal winds over the Indo-Pacific during and after negative IOD event. The influence of ENSO has been removed. This is always tricky. How do you remove ENSO? Lots of debate about that, but if they are not independent, what does it even mean? Okay, so on. So you can see winds here over the Indian Ocean, positive. So these are zonal winds, positive, and here you have negative. So you have the evolution of winds. Essentially you have easterly anomalies going in towards the Eastern Pacific, and you have positive, so stronger trade wind anomalies here, and this is going from Western Pacific as positive wind anomalies, which means easterly winds, so you have to be careful. Positive winds means easterly anomalies, and negative winds means westerly anomalies. Okay, so I hope no. Trade winds are going westward, so they are negative. The westerly wind bursts are going towards the east, so they are positive. X is longitude positive eastward. Okay, and this is looking at D is looking at Indo-Pacific zonal wind signals associated with the IOD in a coupled model experiment, basically arguing that the model captures this and the impact on the evolution of the following years. El Nino, hence the claims about predictability through the spring barrier because of the IOD state in the previous year is a claim that this paper makes, and they argue with model experiments that they can prove it. So you are here looking at longitude time diagram of the equatorial Pacific response to the IOD, external forcing IODs. In the Indian Ocean, it's external to the Pacific Ocean. So you can see how the arguments get muddled. We are saying Pacific and Indian Ocean may not be independent, but now we are saying Indian Ocean is not only independent, but it's an external forcing to the Pacific, and the Walker cell is now treated as independent. Okay, so in the Pacific and Indian Oceans, you have to convince yourselves whether that's right or wrong. So they are looking at thermocline anomalies, and whether these really propagate from the Western Pacific into the so you can see here the end of the Indian Ocean into the maritime continent, into the Pacific. So somewhere here is the maritime continent, but you can see this is the Pacific only now. Sorry, this is the Pacific only, not the Indian and Pacific. Okay, careful. So downwelling Rossby waves, upwelling Kelvin waves in year 0, and you have downwelling Kelvin waves, which are always associated with pushing the thermocline down, discharge, and Birknes feedback to give you El Nino. So you have the upwelling Rossby waves. So you can see that the arrows here are showing current anomalies as well. So you're looking at waves and current anomalies. So that's the zonal current anomalies. Basically, upwelling Kelvin waves have divergence because they are lifting the thermocline, and downwelling Kelvin waves will have convergence because they are pushing the thermocline down. All these things. Basically, jumping ahead to the conclusions, combining IOD and warm water volume influences pushes the 0.8 skill score limit of ENSO backward in time 13 to 15 months before the ENSO peak. If you look at El Nino prediction skills, it's around 0.8, but that's only for 9 months ahead of the peak, which is in DJF, which means after the spring of El Nino year, you have good skill 0.8, and there is a spring predictability barrier, which prevents us from having high skill if you go for more than 9 months lead time. And this claim here is that IOD and the warm water volume can push this skill of 0.8 beyond 9 months into 13 to 15 months before the ENSO peak. This increased predictability stems from the partial independence of the Indian Ocean from the Pacific Ocean. Keyword, partial independence of the Indian Ocean from the Pacific Ocean. The paradigm proposed here also suggests a possible explanation for the biennial tendency of IOD and ENSO. A negative IOD tends to induce an El Nino the following year, which is often associated with a positive IOD favoring a subsequent La Niña. So they are imagining this quasi-biennial time scale of IOD to ENSO to positive ENSO, negative ENSO, positive IOD, negative IOD, and so on. This seems to be confirmed by coupled model experiments, which show a diminished biennial tendency for ENSO when climatological conditions are specified in the Indian Ocean, which means ENSO becomes less biennial if you don't allow the Indian Ocean to respond to El Nino and feed back to El Nino. Are you convinced? Well, that's the paper, so I'm just putting it out there for you. You decide for yourself, because these are tricky when you have few samples, few model experiments, but you don't. We have been saying that El Nino has periodicities of 2 to 7 years. So if you make spectral analysis, it tends to have a quasi-biennial component, a quasi-quadrennial component. People keep arguing that there is a biennial component in it, and they are also arguing the same thing here, but you go figure it. Okay.